Hello friends, so far many mathematics have been done and very slowly but very professionally, ethically and through the realism of mathematical understanding we arrived at the final lecture. This is the unit 4 which we were continuing part C, and again we will be dealing with applications of the partial differential equations. What we do here is a very important thing. Laplace's equation in cylindrical and spherical coordinates, and then we will conclude everything with this title, circular membrane. Laplace's equations has played a vital role in almost all applications of mathematics. We will understand what is spherical and cylindrical coordinates because you know Cartesian two-dimensional coordinates x, y. We know polar coordinates called as r theta, and so now we are in to learn the cylindrical and spherical coordinates. We have the circular membrane at the very conclusion of it. Laplace's equation in cylindrical coordinates is to begin with. This is the equation number 1 which we have studied just now meaning thereby in the previous lecture, or even the lecture we had done about 3-4 days before, or maybe in the 3rd or 4th lecture in this series. This is 3-dimension. If it is a 2-dimension, we call it d2u dx square plus d2u dy square is equal to 0. Cartesian. If it is a 3-dimension Cartesian, we call it d2u dx square as given in 1. d2u upon dy square plus d2u upon dx square is equal to 0 is called as, in Cartesian coordinates, Laplace's equation is represented by this equation 1. Let P is a point whose Cartesian coordinates are x, y, z. 3-dimension, so it is 3 coordinates. And its cylindrical coordinates are given by r, theta, z, r, theta, z. What we mean these r, what we mean by theta, what is z will be illustrated here. This is a diagram, very important, very simple. 3 axes, x, y and z. To be very well understand, you can stand in any center of a room and then look at one corner of the wall, one corner of the room. The partition of the 2 walls facing you, the line joining them going up will be called as z-axis. There is a line, floor and one wall going on right of you, take it as x-axis, and the one which is on the left side of you, as if it is coming to you, will be called as y-axis. Even otherwise you can take other convention also. So this is O is the origin, right, where the floor, the 2 walls of a room meet in a corner is called as the origin. P is a point, x, y, z as shown in this diagram is called as 3 Cartesian coordinates. R, theta, z, now what we are going to call is this notation, where r is the distance between O and M, theta is the angle as shown, XOM is theta. The line M joining the OX will be parallel to OY and obviously will be perpendicular to OX. If you look here, if I draw a line in the same. So, I will be putting x is equal to r cos theta, y is equal to r sin theta and z is equal to z, which is very clear here because the dotted line which is going from M and going to touch the whole OX is 90 degrees. So, r is this, so naturally it will be r cos theta. If you take this triangle again, it will give you r sin theta and z is Pm, that is here. And this is the relation which we have done number of times. Do you remember? If I have x is equal to r cos theta and y is equal to r sin theta square and divide, you get this equation 3. One will give you r square is equal to x square plus y square, another will be given as theta is equal to tan inverse y upon x. Now from 3, we differentiate this r square. It becomes 2r dr dx, I am keeping y constant. Very conventional partial differentiation of polar coordinates, nothing new we are doing. We have done all these things. So, it will give you half of x square plus y square whole to the power half, simple. And 2x is this 2x. This is minus of 1 upon 2 if you look into here, because it is x to the power n form. We simplify it, and what we do is this 2 and 2 cancels. You put x is equal to r cos theta, which you can see in numerator, and then we have this x upon x square plus y square comes down, and so you get x square plus y square is equal to r taken from again equation 3. So, you get x upon root x square plus y square equals to r cos theta upon r. Once again I repeat, in the numerator x you put r cos theta, and the denominator root x square plus y square will become r, and so this r will cancel and we will get this r differentiated with respect to x, keeping y constant, which is written at the subscript of the bracket, gives you cos theta. Similarly, without any calculation, you can understand if r is differentiated partially with respect to y, keeping x constant, you get sin theta. From 3 we go back. 3 means we have substituted r square is equal to x square plus y square, and we had theta is equal to tan inverse y upon x. To remind you, this comes from the very fundamental equation Cartesian to polar, x is equal to r cos theta and y is equal to r sin theta. These two, equation 3 gives like this. So, from 3 we get this. I am now differentiating theta with respect to x. From where? From that relation. Theta is equal to tan inverse y upon x. From there I am getting it. So, we write again from 3. First part we have done. This is the second part. So, we will be getting 1 upon 1 plus y upon x whole square ddx of y upon x. I will tell you what this first term is on the right hand side. It is something like the differentiation of tan inverse x. Tan inverse x is 1 upon 1 plus x square. So, we have the first term 1 upon 1 plus y upon x whole square comes by differentiating tan inverse y upon x in equation 3. Do it on your paper, you will get that result. And then the term y upon x is also differentiated with respect to x to give you this result. Concluding by equation 6, we write minus sin theta upon r. This minus sin theta upon r, as you can see here, this is the d theta dx, and now we have d theta dy. Under similar process we get cos theta upon r. I am doing with respect to y, keeping x constant, process becomes the same. Instead of y, now we have kept x constant. Derivation is not difficult, and so we get this result. It may be noticed that the equation 6 and 7 are obtained from equation 2 and 3. Simple. This is for our reference that we have mentioned. From the chain rule of partial differentiation, the other day, maybe couple of days back or even maybe in the previous lecture, I have talked about this keyword, chain rule. Is this chain rule? Equation 8. Differentiation partially of du dx is du d theta dx du dr dx, because u is a function of, if you go back to equation 1 and equation 2 and equation 3, what I am narrating now, you pick up very easily if you are very clever to understand the partial differentiation. U is a function of x and y, x is a function of r and theta, y is also a function of r and theta. Is it okay? So, r and theta are parameters, 2 parameters. So, the moment we go for more than one parameter, the chain rule comes into play, and this is equation 8 is that chain rule. We have written below, because u is a function of x and y and x is another function of r theta, y is also a function of r theta, and therefore, equation 8 is oriented. That I have explained you. This is the two lines below equation 8 explains what I have said you. So, we obtain du dx equal to, I am putting these values, du d theta is there, d theta dx we have just obtained. Then dr dx is also obtained, we put cos theta, getting this beautiful result. So, du dx is simplified. You get cos theta multiplied by du dr minus sin theta upon r du d theta is equation 9. Equation 9 is a little bit simplified. What we do is, we take u as an operator on this and remove it from both the sides, nothing that extra we have done. So, you get d dx of, the u is there, but we are using it as an operator. We are differentiating u with respect to x. So, I am just removing it. This becomes cos theta of partial derivative with respect to r sin theta upon r like equation 9, and we will have d of d theta partial. And therefore, this whole thing I can write a new, this result is not new, d2u upon dx square can be written as d dx of du dx, second order partial derivative. I will remind you, we have started with du dx is equal to small p, du dy as small q, and here we are having it d2u upon dx square. If you recall, we have called it small r, d2u upon dy square we have called it t. So, the same notations, but the last equation which you are seeing here, this one, is nothing new. I am only defining what du upon or d2u d upon dx square has a meaning in words like this. If I differentiate partial derivative of u with respect to x, again with respect to x, this one, then we will be getting d2u upon dx square, putting the values now. Left hand side remains the same, in the right hand side I am substituting values from 9 and 10, which is just now we have seen. We get this result, cos theta d dr minus sin theta upon r partial d d theta. Then we will be having this as cos theta du dr minus sin theta upon r du d theta. Simple substitution without any rigid mathematics that we have done, no complications, simple d2u upon dx square. From that equation which we have explained just now, we obtain this thing. Solving the right hand side, we get only right hand side. You can see here, I am differentiating with respect to x. So, I get cos square theta d2u upon dr square minus 2 sin theta cos theta upon r d2u cross derivative, and we get, upon some simplification and arranging the terms, equation 11. Same process is repeated again for the variable y, meaning thereby I am now differentiating u with respect to y to obtain the second derivative. Is also written as we have written the other equation, that means d2y upon dx square can be written as d dy of du dy. I will be substituting du dy here. After little bit of solution, I will be arriving at equation 12, same as equation 11 was. We add now the previous equation, that is 11. The equation now you are observing is equation 12. We add them, and notice that the equation 1 with which we have started, this is delta square u equal to 0 is transformed into delta square u is second order Laplacian operator, or second order Laplace's equation will be equal to 0. I am simply substituting these values, adding 11 and 12, certain terms will be cancelled. We finally have 1, 2, 3 and 4 terms. 1 is a second derivative, third term is a second derivative, fourth term d2u upon dz square is also a second order derivative, we get this, which is in a very compact form, takes the shape to be named as 13th equation. We write it as 1 upon r partial derivative of r du dr, that means r is a product of du dr, and all these things, 1 upon r square d2u upon d theta is square, and then we have d2u upon dz square is equal to 0, that is equation 13. This is perfectly in r, theta and z, with which we have started on the very first page of this lecture. You remember it. It is called as what we have written there. I'll remind you. We take a point P, x, y, z if it is a Cartesian, three system coordinates. But if you are going to find the other coordinate system, we have considered cylindrical coordinates, and so we have written it r, theta and z. We have explained, if you look and if you remember at that figure which we have done just now, there were 3 axes, x axis going on my right hand side, y axis coming to me, z axis drifting to the top in front of me. So, we have x, y, z 3 axes, we have taken P, a point somewhere on in the space at the middle of the room, drop a perpendicular from P on the floor, connect with dotted line that you have shown to the x axis, that means the join line of the wall and the floor on my right, and then that becomes a 90 degrees. From there, this equation number 13 has only 3 variables r, theta and z. So, naturally, what we obtained 13 is called as the Laplace's equation in cylindrical coordinates, where that one part is over. We have promised for the second as well, and this promise is like this. Laplace's equation in spherical coordinates will have 3 other coordinates naturally, and this time we will start from that equation 1, if you recall, and equation 1 means d2u upon dx square plus d2y upon ds square plus d2u upon dz square is equal to 0. That is the Laplace's equation in Cartesian coordinates in 3 dimension. The same I am giving here, but with a little difference. X, y, z remains the same. We take a point P, x, y, z that we have taken earlier. Now, in place of this x, y, z, at the point P, we write this r, theta, phi. You read this line. Let Cartesian coordinates of P is given by x, y, z. The polar coordinates will be r, theta, phi. R, theta, phi are defined very clearly. Exclusive presentation of r, theta and phi. Look here. Same thing. From a point in the space, drop a perpendicular. We call the foot of the perpendicular as M. By dotted line, you join P to the corner or to the line joining wall and the floor to your right. It becomes a 90 degrees obviously. If you drop a perpendicular from here at this point and join it straight, it will be a 90 degrees. The angles separating at 0 are 2. One is phi made with the x axis, another is theta made with z. Theta is the angle between z axis and the line joining that point in the space, that is P, to the corner of the whole 2 walls and the floor where you are standing. The 2 floor, one is on your right, the other is in front of you, and the line joining of the 2 walls going up vertically. So, that is theta. The distance between O and P, that means from here to this point space, you can measure it by r. From O to M on the floor, you make it again r. So, the polar coordinates are given by r, theta and phi. We have substituted there x is equal to r cos theta and y is equal to r sin theta, and if you recall, we had derived 2 equations from there. One is r square is equal to x square plus y square, another is theta is equal to tan inverse y upon x. We do the same process. The only thing is, instead of r and theta, there is an additional angle. We call it phi. We defined phi. So, equation 14 is that the one which we had in the other part. We say x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta. Similar, no problem, no ambiguity. We square and add like the one we have done earlier. You get r square is equal to x square plus y square plus z square. Is it okay? We get phi is equal to tan inverse y upon x. To remind you, there we used to have theta is equal to tan inverse y upon x. We go further. And the second is theta is equal to tan inverse y upon x will now be converted into equation 17. We will write it tan inverse root of x square plus y square upon z. We repeat the same process without putting into your mind any confusion. We have done there dr dx keeping y constant, dr dy keeping x constant, and dr dz keeping x and y both constants. So, we get dr dx is equal to sin theta cos phi. Dr dy we obtain is sin theta sin phi, and dr dz is equal to cos theta, all partial derivatives. I again repeat, in the first case we kept y and z constant. In the second case dr dy, we have kept x and z constant. In the last, when dr dz is required to be obtained, we have kept x and y both constant. Further, we have now I am differentiating theta with respect to x, I am theta with respect to y, and I am differentiating theta with respect to z. Method remains the same as we have done in cylindrical coordinates. We get d theta dx equal to cos theta cos phi upon r. We get d theta dy cos theta sin phi upon r, and then we have d theta dz minus sin theta upon r. Do you recall that this line using chain rule? We use it here again. Previously, it was u is a function of x, y. Now, we will be saying it u is a function of x, y, and z. So, one more term will be added. If it is x, y, z, and w, another two terms will be added. So, we have done the same theory. Chain rule is written as du dx, du dr, dr dx, du d theta dx, and finally, it is with respect to phi, writing it this equation. We substitute all values possibly that we have obtained in the previous equations, and you get du upon dx like this. I have mentioned here, this is similar to the equation 9 that we have obtained. When you go back, shut down your computers, close your books, you will be finding by solving with a paper and a pencil that if you use straightway 9, you will be getting this equation which we have ended just now. What happens that we then find d2 upon dx square, d2u upon dy square, as we have concluded in equation 11 and 12. Also find d2u upon dz square. Calculations we do not do, it has been done in the previous or preceding sections. And like the one we have obtained in 13, we obtain here 1 upon r square ddr r square du dr plus 1 upon r square sin theta minus all that thing plus is 22nd equation. This is the Laplace's equation in spherical coordinates. Three coordinate system that we have studied. I want to conclude, I want to summarize everything in one line. Cartesian coordinates is denoted by P. I will also draw your attention to two figures that we have drawn. Cartesian coordinates P, coordinates are x, y, z. When I am talking about cylindrical coordinates, I will have r, theta and z. Notations are self-explanatory. When I will be using the polar coordinates or concluding the spherical coordinates, I will be using it r, theta, phi, drawn in the figure extensively. Very exclusive representation that we could draw. The figure x, y, z, x is 3 dimension and 22 is obtained. we have concluded two things: Laplace's equation in cylindrical, Laplace's equation in spherical coordinates. Coming to circular membrane, two-dimensional wave equation that we have studied earlier in the previous lecture as well, when we were talking about the D'Alembert solution, is this. And note that if it is a 3-dimension, I will be getting d2e upon dx square plus d2e upon dy square plus d2e upon dz square. That is the only thing. You can go up to n dimensions, no problem. Which when changed to polar coordinate system, we get this. Polar coordinates again is the same thing. R theta is the polar coordinates. So I will be getting d2u. Let the boundary of the membrane is a circle of radius a. Let gr theta is the initial velocity of the membrane and function of r theta is the initial displacement. Hence, this function u is a function of r theta t, r is the radius vector, theta is the vectorial angle, t is the time, and satisfies the following boundary conditions. One is boundary, another is initial conditions. We will obtain the previous equation and we substitute these. R is a function, f is a function, t is a function in 28, and I have written that they are functions of r theta and t only. The 23 after substitution of this all becomes, and the variables are separated, it is integrated, and therefore we assume that this is equal to m square. The ordinary differential equations for r, f and t are given by this 31, 32, 33 and 34, where we conclude. Then we have s is equal to lambda r substituted in 31, we get these results. 37 is very easily obtained, and eventually we form the Bessel's equation, which we have studied in the previous lecture. We have studied there j and x and j minus, here we have the integer m, makes no difference therefore, and we conclude the solution of 24. That means the circular membrane that we have started is arrived at the equation 40, and with these independent of the theta solution is written eventually and finally as the concluding relation named as 41. So that all marks the end of the application of partial differential equations. We have done so many things, D'Alemberts, we have done one-dimensional wave, two-dimensional heat equation, then spherical and then cylindrical, and finally to circular membrane. Well, let us summarize and let us see what we have done. While summarizing everything that we have done, it's an immense pleasure that we have so many beautiful keywords, nomenclatures that we have done. Started with heat equation, but behind of everything we have the application of partial differential equations. First thing we have done heat equation, then switched over to a very important thing, Laplace's equation in cylindrical and polar coordinates or in spherical coordinates. And then finally we ended up with circular membrane. But what we have noticed is that its representation in a finer way through geometrical aspect. We have taken a point in space, we have dropped a perpendicular from there, we have designed what could be the angle theta, we have designed what could be the angle phi, we have designed what is a radius vector, we have told that what could be r theta and z, r theta and phi. We have named them individually, calling them as cylindrical coordinates and spherical coordinates. What we mean by the changeover from Cartesian to polar, and then three coordinates as we have seen, r is equal to, or x is equal to r cos theta, y is equal to r sin theta. We have said here x is equal to r cos theta sin phi. You will appreciate the increment in variables and how we adjusted all these three variables, two variables in arriving at the conclusion. That means we obtained this Laplace's equation in spherical and cylindrical coordinates, and eventually we obtained so nicely framed, beautiful looking the circular membrane. This is all geometry. The circular membrane depends on two things. One is a boundary value problem, another is initial value problem. In other words, they are called as boundary conditions and initial conditions. Looking beautiful, if you appreciate. Go back, draw them on your paper with a pencil, you will appreciate the beautiful mathematical analysis that it involves. My pleasure with you all, and I believe you shared as well the pleasure of doing mathematics, do more mathematics, at the same time understand mathematics, find the beauty in it, find the meaning of it, learn the abbreviations, learn the notations, and learn so many terminologies that involves mathematics. Thank you for being with me.